Welcome to the another lecture of Design of RCC Structure. In this class, we are going to discuss about doubly reinforced beam and we will analyze it. First of all, you have to understand what is doubly reinforced beam. What is the meaning of doubly reinforced beam? In previous lectures, you have already learned about singly reinforced beam. So, doubly reinforced beam is a type of beam which has reinforcement in tension zone as well as reinforcement in compression zone. As you have learned in previous lecture, which video link is given in description box, about singly reinforced beam, the reinforcement which is given in tension zone, bottom zone. But in that case also, we have provided reinforcement in upper portion, but just as anchor. So, to make the mesh, to bind up the stirrup, but the purpose is only to make the mesh, only to bind up the stirrup. There are no other purpose. But in this case, in case of doubly reinforced beam, in compression zone, reinforcement also given as per design. So, it is clear that this is the basic difference in single reinforced beam and double reinforced beam. Design reinforcement in single reinforced beam is given only in tension zone, but in case of doubly reinforced beam, design reinforcement is given in tension zone as well as in compression zone. Now you have to understand when to go for doubly reinforced beam, when we have to decide that we have to design a doubly reinforced beam. When applied ultimate moment mu is larger than limiting moment mu lim, we have only two choices, either increase depth of section or provide compression reinforcement. But due to various restrictions, only choice is to provide compression reinforcement, thus giving rise to doubly reinforced beam. That means the main basic concept is when depth is restricted in any design, maybe due to aesthetic purpose, maybe due to architectural purpose, maybe due to any other purpose, but when depth is restricted of a beam, mainly in that case we have to provide doubly reinforced beam to carry the total moment. Okay. The assumptions are same as single reinforced beam. So, next I want to discuss the condition, which I have already told in previous part. Now, in case of mu greater than mu limit, that means the total moment which comes in a section is greater than the limiting moment, and that is due to only depth restriction. So, in this case, excess moment will be carried by additional reinforcement. Look, this is a graphical representation of cross section of a doubly reinforced beam. In figure 1a, you can see here a doubly reinforced beam. In tension zone, there was 5 reinforcement bar, and in compression zone, there was 3 reinforcement bar. So, if we divide this graphical representation in two parts of single reinforced beam section and additional reinforced due to extra moment, then the figure will be like this. It is to just make you understand better. Okay. So, for mu limit requirement, the single reinforced beam section is like this figure 1b, only 3 bars, and this area of steel is denoted by AST1. That means AST1 is area of tensile reinforcement for single reinforced section, and for extra moment we have to provide additional reinforcement, that is shown in figure 1c. You have see there are two extra additional reinforcement in tension zone, that is denoted by AST2, and additional reinforcement in compression zone, that is denoted by ASC. So if we add these two, we will get the figure 1a. Area of compression reinforcement is denoted by A suffix SC, and total area of tensile reinforcement is denoted by A suffix ST. Now for AST2, which is additional, for AST2 and ASC, to find out this formula is given Annex G of IS 456-2000. For AST2, the formula is ASC into FSC by 0.87 Fy, and for ASC, area of steel in compression zone, for compression reinforcement, that is equals to mu minus mu limit by FSC within bracket d minus d dashed. Let's go to Annex G of IS 456-2000. You can see there this formula is already written, and there are a few new terms, FSC, d dashed. I am going to discuss this after seeing the Annex G. Okay, so let's go to the code. So as I told, Annex G, in Annex G, look in G 1.2 section with compression reinforcement, that means doubly reinforced beam. For the doubly reinforced beam, the formula what I have write, you have seen earlier. This formula is given in first equation, and another formula is given in just above G2. So these are already given in Annex G. Let's go to notes again. Let's start the analysis of doubly reinforced section with the help of strain and stress diagram. The strain and stress diagram is very common to you. You have already seen this type of diagram earlier in the video of singular reinforced beam analysis, which link is given in description box. You can go through this. Now see the cross section, and figure 2a, there are 5 tension reinforcement in bottom tension zone and 3 compression reinforcement in upper portion. Now look at figure 2a. B is width of the beam, small d is effective depth. You know what is effective depth of a beam. From top to the center of tension reinforcement, the total depth is called effective depth. Now in right side you can see here is a demarcation, and it is written that d dashed. D dashed means the effective cover to compression steel. Okay, here is d dashed, effective cover to compression steel. So the rest amount is d minus d dashed. Now see figure 2b, that is strain diagram. Before that, you know the depth of neutral axis is denoted by xu in limit state method. Now strain diagram just like as singular reinforced beam. You can see the strain diagram, and value in upper portion and value at bottom portion, and at right side this is the stress diagram. You can see the values are same, 0.45 FCK, 0.42 XU, and here is the tension 0.87 FY. This value comes from the assumption in clause number 38.1. The video about that is already in this channel. Go to description box, you will get this video. So, but what is extra in this doubly reinforced beam? That is C2. So C2 is compressive force carried by compression steel, and C1 you know just as earlier, the compressive force carried by concrete area. So top to C1, this depth is 0.42 XU. This is also as per clause number 38.1 of IS 456/2000, which we have discussed earlier in the case of single reinforced beam design. As I told you, the assumptions are same. We have to just know the extra things. Now the lever arm is, you can see lever arm is denoted by A, and the lever arm is D minus 0.42 XU. This is clear. So the term which we have get here, let's again discuss. Small d is effective depth of beam, small d dashed is effective cover to compression steel, ASC is area of compression steel, AST is area of tensile steel, XU is depth of neutral axis, C1 is compressive force carried by concrete area, C2 is compressive force carried by compression steel, small a is lever arm, which is equals to D minus 0.42 XU. So these terms are already written here. Okay. The another term I told you that I will discuss here. So FSC is F suffix SC, that is equals to stress in compression steel. Okay. So FSC, the important term here, this is equals to stress in compression steel. Now total compression C is equals to C1 plus C2. You have already know what is C1 and what is C2. Now we know C1 is 0.36 FCK into B into XU, and C2, the compressive force carried by compression steel, that is equals to stress in compression steel, that is FSC, into area of compression steel, that is ASC. So C2 is FSC into ASC, and total tension T is equals to 0.87 into Fy into AST. So by equilibrium equation, total compression is equals to total tension. So if we put the value of total compression, that is 0.36 into FCK into B into XU plus the C2 part, that is FSC into ASC, that is equals to total tension. Now the moment calculation portion. So total moment, that is mu, is equals to mu limit plus the additional moment is mu2. So we know mu limit is equals to C1 into lever arm, that is A. So mu limit is equals to 0.36 FCK into B into XU into within bracket D minus 0.42 XU, and mu2 is C2 into lever arm A. So mu2 is equals to FSC into ASC into D minus D dashed. So from this equation we can get the formula for mu, that is equals to 0.36 FCK into B into XU into D minus 0.42 XU plus FSC into ASC within bracket D minus D dash. This is the formula to find out mu for doubly reinforced beam. And note one thing, to determine F suffix SC, that is stress in compression steel, follow table F of SP16, the design aids, for given grade of steel and D dash by D ratio. So let's go to SP16 table F to understand this note. Okay. So this is table F of SP16, the design aids. Table F, stress in compression reinforcement FSC in Newton per mm square in doubly reinforced beam with cold work bars. Fy is given in Newton per mm square for 415 grade of steel and 500 grade of steel, and ratio D dash by D is given So there are few ratios are given 0.05, 0.1, 0.15, 0.2. In this case we don't have to interpolate, just if we get any fraction value, just take the higher one. If we get any value between 0.05 and 0.1 for d dash by d ratio, just take the upper value of 0.1. So this is the table, is very important, which you will use for short answer type problem also and design problem also. Okay, let's solve a short answer type problem to understand the analysis of doubly reinforced beam. Okay, and this is an analytical problem, not design. Okay, so the question is, determine the factored moment of resistance of a beam 230 mm by 460 mm effective. The beam is reinforced with two numbers of 16 mm diameter bars on compression side and 4 numbers of 20 mm diameter bars on tension side. The compression bars are placed at a distance of 40 mm from top. Use M20 grade of concrete and Fe 415 steel. As I told you every time, to solve any problem, read out the problem several times. Okay, so as per the problem, let's first draw the section. This cross section is not given in question, so you have to draw it to understand better, like I have drawn it. So as per question, I have drawn the cross section. The width is 230 mm, the depth, the effective depth, that means from top to the center of tension reinforcement, the effective depth is 460 mm. In compression zone, there are two numbers of 16 mm diameter bar, and from the top to the center of the bar, the distance, that means small d dashed is 40 mm, and in tension zone there are 4 numbers of 20 mm diameter bars. So write down the given data, which is already given, that is B is equals to 230 mm, effective depth D is 460 mm, small d dashed is 40 mm. So from this we can find out the area of steel. So area of steel ASC, in that means area of steel in compression zone. In compression zone there are 2 numbers of steel, so 2 into pi by 4 into 16 square, the diameter of bar, that is equals to 402 mm square. Now next we have to find out AST, area of steel in tension zone, that is equals to 4, that means the number of bars, into pi by 4 into d square, d is here, d means diameter, here is 20 square, that is equals to 1256 mm square. FCK is given, that is 20 Newton per mm square for M20 grade of concrete, and Fy is 450 Newton per millimeter square for Fe 415. So from this we can check out the d dash by d ratio, that is equals to 40 by 460, that is equals to 0.087. So definitely to find out FSC from the table F of SP16, which you have seen in this video already, so we have to we know there no values for 0.087, there is a value for 0.05 and there is a value for 0.1. just like I have told earlier, we have to take the higher value, so we have to consider for d dashed by d is equal to 0.1 from table F of SP16. So the value of FSC is equals to 353 Newton per millimeter square. Now from the formula we have to find out the depth of neutral axis, that is XU, is equals to 0.87 into Fy into ASC minus FSC into ASC by 0.36 FCK B. So if we put the all values like 0.87 for Fy 415, for ASC 1256, minus for FSC 353, for ASC 402, and by 0.36 for FCK 20 and for B 230, we will get the value of XU, that means the depth of neutral axis from the top, that is equals to 188.15 mm. Now for FE 415 from clause number 38.1, just below the table, we get the value for XU max. For FE 415 grade, XU max is 0.48 D as per IS 456 2000. That is equals to 0.48 into 460, that is equals to 220.8 mm. So XU greater than XU max here, hence the section is under reinforced section. For factor moment of resistance, we have to put the formula. Now, mu is equals to 0.36 FCK into B into XU into within bracket D minus 0.42 XU plus FSC into ASC into within bracket D minus D dash. Now let's put all the value, you know the all values of these abbreviations. So put all the values, you will get the answer that is equals to 178.3 kilonewton meter. So here the problem is end. That's all for this lecture. Thank you.